talk about reinsurance, which we started on Friday. And then, assuming I've got a little bit of time at the end of reinsurance, I will say a little bit about the class test and assignment 1, which I have a copy of here. And then we'll do aggregate claims amounts under reinsurance tomorrow. If I don't have time to talk about the class test and the assignment today, I'll do that tomorrow. So somewhere between reinsurance and aggregate claims, under reinsurance, I will talk about the class test, which is a week today, and the assignment, which is due in a fortnight today. So reinsurance. So at the end of the last lecture, we talked about 2 types of reinsurance. One was excess of loss reinsurance. So we had the amount X was the claim amount, Y was the amount paid out by the insurer, which was X if X was less than M, and it would be M if X was greater than or equal to M. We also had the amount paid out by the reinsurer, which was Z, which was 0 if X is less than M, and it would be M minus X if X is greater than or equal to M. We also had proportional reinsurance, where Y was alpha X and Z was 1 minus alpha X, where alpha was the retention level, which was between 0 and 1. So what are we going to do today is ask what is the expectation of Y, the amount paid out by the insurer, and Z under these cases. Maybe what is the distribution of Y, or Y over there under these cases. And what else will we do? I'm going to introduce another distribution, which I'll talk about in a moment, because it's sometimes useful. So this is the definition. So what is the expectation of Y? That's what we're going to start by looking at. And that's on slide 15, I think. Let's go to that. So we're assuming in all this work that we're told the distribution of X. This is the loss distribution, the total claim amount. So, and we're going to ask about how does Y, distribution of Y, its expectation, relate to f of X or E of X, etc. So there's only one loss distribution here, and maybe it's worth just drawing it. It will be a loss distribution. So it will be on the positive real line, and it will probably be positively skewed. So this is f of X. It could be, and we probably need to write a little X there, because we'll want to talk about maybe f of Y, but everything will be related to f of X. So you've got some data, you've decided that it's a Pareto distribution, or an exponential, or a gamma claims. We know how to work out the expectation of f of X. It's the integral from 0 to infinity x f of X dx. We now introduce Y. It doesn't really matter where I put the I did pause, I made it inconsistent here. It doesn't matter where I put the equals here. In fact, it's the other way around. I thought, oh, which way around should I do it? But it doesn't matter because they agree. At x equals m, then y equals x equals m. So you don't have to worry here about that. So what will be E of y? Well, what is the distribution of y? Well, from 0 to n, it's exactly the same as x, yes? So if x is less than m, the distribution of y is exactly the same. If x is greater than m, then y equals m exactly. So there is a probability that y will equal m. So the probability that y equals m will be equal to the probability that x is greater than m. So if x is out here, then y will sit here. So this thing here will be of a height equal to p of x greater than or equal to m. Or it doesn't matter, let me keep consistent. So what is e of y? Well, it's the integral from 0 to m x f of x dx plus m times p of x greater than m, which is what I've written up there. So it's the same definition. We're going along what value, what's the density at x? It can take this, 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 and when we get to m, then we have a probability. So this is this other type of mixture. Y is continuous up to m, and then it's a discrete mass at m. So this is what it looks like. It's continuous, and then we have a spike of size equal to that probability. So that's from first principles. Now, this can be difficult. Sometimes you can do this straight away. If you can do this integral, fine, but it's sometimes difficult because it's an incomplete integral from 0 to m. This thing should be not so bad. It's a survivor function. This is the survivor function for x. So hopefully if we have the CDF, we can work that out. So we could, for some examples, the exponential is 1, although I'm going to show you how to do it in a different way. You could just put in, we know what this is the e to the minus m lambda, and we could do that integral, the incomplete integral by parts, and we get the answer. However, there is another approach, is to try and get rid of that incomplete integral. And that's what we're going to try and do now. So how might we do that? Well, one thing is, of course, to try making this to infinity and then subtracting the bit. So an integral from 0 to infinity gets rid of it, but then we'd have to subtract an integral from m to infinity. You might think, well, I've just made the problem no easier. I've put this to infinity and I'm now subtracting something from 0 to infinity. But it turns out with a little transformation I can improve the situation. So here I've done exactly what I said I would do. I've made the first integral go from infinity to infinity, so I've added too much in, so I've subtracted it here. So these two together is still the integral from 0 to m, x f of x dx. And what have I done here? I've written the survivor function as an integral of f of x. So this is by definition the integral, the probability that x is greater than m, and there is an m. That then means I can see, well, what have I got? I've got e of x here, so that's something I hopefully know. It's a loss distribution. If it's exponential, it's 1 over lambda. If it's Pareto, it's delta over alpha minus 1, etc. And I've got this integral, because I've got an x here and an m here. So I haven't made it any simpler yet, because that's still an incomplete integral. But what I can do is a substitution, and I can replace z, define z to be x minus m, which is the amount paid out by the reinsurer, in fact, and do the transformation. So this becomes z, this becomes f of x evaluated at, well, what is x? It's z plus m. What is the Jacobian of this transformation? Well, it's 1, so it's not there, but you should ask. We should be, what is dz dx? So dz equals dx. So that's it. And so now we've got a complete integral again. So that might be an easier way of working it out. So I've given you two ways. The one that's gone off the top here, or this way. Why this might be easier is it's because it's a complete integral. And I'll show you two examples where it is easier. It turns out that this, of course, has to be, by definition, f of e of z, because we know that x plus y, y plus z must equal x. So in some senses, this is going to be e of z. Now, just to confirm yourself, what is the distribution of z? Well, z is slightly different, but if we were going to draw the PDF of z, what would it look like? Well, it would start here. When x was the value m, z would be 0, and then it would have this tail. So, and so z would be equal to a point here. So z is 0 whenever x is less than m. And when x is greater than m, z follows this distribution with the same shape. So, but rather than starting at n, it starts at 0. So that's what we're doing. And this expectation just has a term missing here, which is 0. So to get the definition, we would do 0 times the probability that less is x in m, plus this curve here, which is f of x, but it's not f of x starting at 0, it's f of x starting at m and going onwards. So starting at m and going onwards. So I've just shown, in some senses, by definition from the sum that x plus y equals z, this must be e of z, but I've just related it back to first principles by integrating this over the possible values of z. So let's do this for 2 examples. So let's start with the simplest loss distribution, which is an exponential. So it's got an exponential k, and after a certain point, we are going to ask for reinsurance. So do I need to draw that again? So if you want to, and you might like to just check this, we can go back here and do it from first principles. So we'd have e to the minus lambda m here, and we'd have lambda e to the minus lambda x here, and we would do this by parts. So you might like to check that. Alternatively, we can use what I've just derived, and I'm arguing that this is going to be slightly quicker because all the integrals just drop out. So we've just derived it, we've just shown that e of y equals this times this integral here. So I've got to do this integral when x, the original loss distribution, is exponential, so that's lambda x minus lambda. But now we're not evaluating it in the x, we're evaluating it in z plus n. So I need to do that integral. I'm going to do an integral with respect to dz, so let's get rid of anything that doesn't depend on z. So we get out an e to the minus lambda m comes out, and we get that. And if we look at that, what does that look like? Well, it's not the core of an exponential, in fact it's the expectation of an exponential. So immediately we can look at this integral, you could do it. All these tricks with cores, you can in fact do from first principles, but I advise you to just look here. This is the exponential integrating from 0 to infinity z, so that's going to be e of an exponential with rate lambda, so that's going to be 1 over lambda. So that's that. So this is what I've got. So this is the expected value of y, is 1 over lambda, 1 minus e to the minus lambda m. And just to get a reality check, e of y will be less than e of x. And if you look back, so just to check you've got this, e of lambda, this is e of x, and so what have we got here? This will be this will be less than 1 because we're subtracting a positive thing. So it's y. It will always be less than 1 over lambda. So e of y will be less than e of x. So it doesn't mean I've got the calculation exactly right, but at least I can check. It sort of makes sense. There is a decline here in e over lambda. Okay, I think the second example is Pareto. So again, I could go back to the first principles and put in a Pareto. So again, if you want to do this, you could put a Pareto here, but you'd have to do the incomplete integral. It would be a bit of work, more work than for the exponential. And we do have the tail, the CDF of the Pareto, or the tail function of the Pareto, which we go in. But maybe it's going to be easier to use this method. So again, when in reinsurance, you're always having this underlying loss distribution. The only distribution that you specify or you start with is the original loss distribution. So this is a Pareto. So there's the PDF and the mean of a Pareto. So if I've got reinsurance with retention M, then I can take the E of X minus this E of Z term. So I'm just going to work out this, which is E of Z. So it's going to be this integral, because remember it's the PDF of the loss distribution evaluated at Z plus M. So the X will be replaced by this here. This looks like a bit like the PDF of a Pareto, but with parameter lambda plus M. Yes. So if you look at this, it's a Pareto with parameters alpha and lambda plus M, but with a Z there. So it's going to be the expectation. So this is going to be related to the expectation of a Pareto with parameters lambda plus M and alpha. So what do I need? I need to have the PDF of that Pareto here, which is what I've got here. So what don't I want? Well, I've got a lambda alpha I have to take outside, because that's not part of the PDF, and I've added in a lambda plus M to the alpha, so I need to take that outside. And so then I can see that this is the PDF of a Pareto with parameters alpha and lambda plus M. What is the expectation of that Pareto? Well, it's the first parameter, lambda plus M, divided by alpha minus 1. So again, I was thinking I would have to do an incomplete integral, and at the end all I've done is inspect an integral and written down the answer. So this is E of Z, so we have to subtract it from lambda alpha minus 1, so we get a 1 here. If I take out an alpha minus 1 and a lambda here, it ends up with one of these cancels with here, so we get this alpha minus 1 term. So that's the expectation of Y. And again, a quick check, sort of makes sense. I can believe this. I've got the original expectation of X being reduced by a certain amount because of the reinsurance. So, if we wanted E of Z we've calculated in these cases. Now, there is another distribution I'm going to introduce, which is the reinsurer is not often told of, or is not usually told of the claims that they're not involved in. So the reinsurer only gets to see claims greater than M. So they don't get to actually see the Z distribution. They don't see this. They only see a distribution of the claims they see. So if, for example, Z looks like this, 0, 0, 0, let's say M is 1,000. So they then see 100 because this was a claim well, maybe I should put the X's up. So let's say there was a claim of 900, 700, 200, and then 1,100. And then 1,700, and then 400. The Zs would be 0, 0, 0, 100, 700, 0, blah, 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 blah. So if I'm the reinsurance company, I'm not normally told of the ones that I don't see. So there's another distribution, which we're going to call W, which only sees 100 and 700. So the reinsurer, if they're going to try and estimate things, they might like to try and estimate the original loss distribution. But what they only see is the claims greater than 1,000. So the question is, what does that distribution look like? So, rephrasing that, in this, the reinsurer doesn't often see, only has information about doesn't see the losses smaller than M. So they get a different sample of claims. What is the PDF of W, the amount the reinsurer will see, given a payout? So given the reinsurer has to pay out something, what's its distribution? Well, I'm going to derive that from first principles, but again you can see that it's going to be a distribution that's related to this. So if you think about it, they clearly pay out from 0 to this. It's going to have this form, because clearly this is they pay out more up here than here, but it's going to be renormalized so this integrates to 1. So I'm going to prove that mathematically, but perhaps you can see it from just the argument that we're interested in now, not in a distribution where the mass has been put at m, it's where it's been truncated. So it's a truncated distribution. It's the distribution of z given it's greater than 0. So what is the distribution of z given it's greater than 0? Well, it'll have the same shape, but it'll have to integrate to 1. So this is how we prove it. But it's going to give you the answer that I've got from the picture. It's going to look the same of f of x, but it's only going to start at 0 and go off to infinity. It's going to integrate to 1. So in this case, and sometimes it's easier, when you're trying to derive PDFs of things, you're asked to derive the PDF. Sometimes it's easier to work with the CDF and then differentiate at the end. So again, if you're trying to do a transformation of variable, you could try and work this out, but this is a very messy transformation, this W. So maybe it's better just to do the CDF. So what do we answer? Well, the CDF would be the probability that W is less than some little w. What is W? Well, it's going to be the probability that Z is less than W given Z is greater than 0. We don't even know, we don't have any distributional information about Z specified. We need to turn this back into X. So we know that Z is X minus M. So that's what we get here. So we then rearrange this because we want a probability statement about X. So we've rewritten this. The probability distribution of W is in terms of X. So W is less than little w if X is less than W plus M, given that X is greater than M. So this is A given B, A given B. So A given B can be written as A and B divided by the probability B. So I'm using this result that says the probability of A given B equals the probability of A and B divided by the probability of B. So that's a standard result. So A will be, so what's the probability of both of those things? So that's the probability of X being between M, easier to point here, isn't it? The probability of X being between M and W plus M. So that's this integral. Or I could have written it straight down like this. You might have seen, might be easier. This is the probability that X is between M and W plus M, divided by this thing here. So what's this? This is again the probability that X is greater than M, which is this term here. So that's the CDF of W. Then I have to differentiate this with respect to W. So this will disappear because it doesn't depend on W. This stays on the bottom. We've got a W here, so differentiate this with respect to W will give us a little f of x. So we've just proved what I did in my pictures, that this is the PDF of W. So it's the original loss distribution shifted along by n and then normalized, which I said was pretty obvious if we thought about it. So that is the distribution seen by, for the ones that just are seen by the reinsurer. So now we might want to, let's go back and look at our example. What about the exponential? So if the reinsurer, what will the distributions of claims coming into the reinsurer look like if the original claims follow an exponential with rate lambda and the retention level is n? So they won't see any of these zeros, they will just see claims greater than n, and they'll only see the amount greater than n. So what will it look like? Well, we've derived the first principles, so it's going to be, they don't quite fit on the slide, do they? Just get them both. So it's the PDF of the exponential, which evaluated at w plus m, divided by the tail function. And then with a little bit of thought here, you see we've got a minus lambda n here and a minus lambda n, so they cancel. So turns out that the exponential distribution losses, if you do this truncation, the distribution will also be exponential. don't know if you knew that, but an exponential distribution is the only distribution where if you cut an distribution at any point and look at the distribution beyond that point, it's still exponential. So it's a way of defining the exponential. What is the distribution where if I truncate it, it still looks the same? So if you think about the exponential, what we're saying there is if we do this, we truncate it anywhere and just look at this bit, it'll also be exponential. It's also exponential when I do the renormalization. And so this is called the memoryless property of the exponential distribution. We'll see in the next section, maybe I'll just say this now, we'll see in the next section exponentials are sometimes used for waiting times, but it's a little, if you think exponential distributions model waiting times, it's rather disappointing because it means if you've waited for an hour, you're no more likely to be served than if you turned up, because the distribution waiting times are the same. So if you do hitchhiking and you believe that it's a memoryless process, if you've stood there in the cold for 2 hours, you're no more likely to get a lift than when you turned up. Which is perhaps right with hitchhiking, but buses, you hope that if you waited for 10 minutes for a bus, the next bus is more likely to come in the next 10 minutes than before. So the exponential distribution has this property that it's memoryless. What about and it's the only distribution that is memoryless. So it's one way you could define the exponential distribution. So let's look at our other example, which was the Pareto. There's nothing to say when you start this what you're going to end up with, but here we do end up with a Pareto, but it's not the same Pareto because we wouldn't expect it to be memoryless, or it can't be memoryless. So just to point out, this is the PDF of the Pareto, but evaluated at W plus M, which was the thing on the top. This is the survivor function of the Pareto. Remember, f of W has to be a density, so by definition, because we've used this conditioning rule, it's going to be a density. The question we're asking ourselves is it something we recognise? And here it is something we recognise. It's another Pareto, but with parameters changed. So there is some memory here because it knows that we've, if you're thinking it was a waiting time, it knows that we've waited m because it does contain some n in here. So that tells us something about we're starting at m. So it is memoryless. It's not memoryless. In fact, it has the interesting property that it goes the wrong way for waiting. So what will be the mean waiting time here is lambda plus m over alpha minus 1. But in fact, it's got bigger. So if you know you're past n, that's the same thing with this heavier tail. If you know you're past n, it's going to be more distribution. It's gone up a bit. Okay. So that's excess of loss reinsurance. So we've worked out, we've got an original x, we have a y, a z, we sort of know the relationships between the x, the y and the z, and we threw in an extra w, which is this where the reinsurer doesn't see the claims, just the ones they see. It can, just as an aside, although I won't expect you to remember this, but you may use it, it could also be thought of, this situation, as when you have excess in an insurance policy. Because if you have a £50 excess, so it makes it more complicated. You may know you can pay out insurance where you will pay the first £50, and then the insurer will pay over the excess. And what happens is usually, well, maybe it's a bit more than that, they say it's £300. Often, if you dent your car, you get a quote, you see it's for £250, you don't tell your insurance company. It's not quite legal. So, in insurance companies operating this excess, what they often see is, and it's not quite as pure as this example, because they'll only see the claims that are greater than the excess amount. It's not so clear because, of course, insurance companies, they may make a claim and then discover it's less than the excess, and so they may see some of them. So it's not as pure as this, but if you go and start working in the area of short-term insurance contracts with excess of where the client will pay in excess. You have to be a little careful that you don't actually see the loss distribution. It's slightly contaminated by not everything being reported to the insurer. Okay, so I did excess of loss insurance first. Proportional reinsurance, things are much easier. Immediately here, the insurer gets to know everything, so there's no W to worry about. Here, if the claim is £10, the insurer gets to know it because the reinsurer will get to know it because they may be paying £1, say 10% of it. If it's £1 million, the insurer will get to know it. So there's no W here. And these are very simple relationships. And so it's easy to work out. If you know the distribution of X, it's very easy to work out the distribution of Y. And we've done that a few times. It's a transformation. In fact, it was on a problem sheet. Do I say what problem sheet it is? Yes. So we did it for exponential. But it's an easy transformation. If you have f of x, what is f of y? Well, f of y will be f of ax d by dx. Jacobian. And the same was said. So if losses are exponential, then you show, it's quite easy to show that if x is an exponential, then y's will be exponential with a rate parameter like this, lambda over alpha, and of course the z's will look like this. And you can sort of see, what is the mean of this exponential? Well, the mean of this exponential is alpha over lambda. The mean of this exponential is 1 minus alpha over lambda, which added together will equal to 1 over lambda. Okay, so I think that's a good place to stop. What we're going to do now, tomorrow, we'll look at, this was all loss distributions. So this was asking about what's the distribution of x. So of course we don't normally look at x, we look at s's. So tomorrow we'll start to look at the aggregate claims of them. Okay, so which order should I do? The multi-choice class test will be here in a week's time. There is a mock class test on the blackboard. I'll put the answers up soon so you can try them without the answers. The test, apart from the questions, I always say the test will look identical, but I don't mean that. So it'll look, the front will be identical and the questions will be similar structure. They will cover everything of the course up until the end of the bit I haven't shown you, so the end of tomorrow's lecture. You can use a calculator, you can use your tables, and you can, if you're not a native English speaker, you can use a dictionary. If you can try and be here promptly, well, I guess we don't get thrown out, so usually I have a class test in the middle of the day, but I guess. So let's try and start promptly at 5 o'clock. I don't think there's much more to say about the class test. Is there any questions about the class test?
How many questions will be there?
Sorry?
How many questions will be there?
The same, is it 15? Yes. So, whatever's on that, I think there's 15.
Nice.
Okay, so the other thing, which is, there's no problem class this week, and there's no problem sheet. There is an assignment, so the assignment is due in this lecture 2 weeks today. The sheet is here. If you want a hard copy, you can take one in a moment. It's basically, you'll look at it, it's very similar to the problem sheets. So really it's a problem sheet that you're handing in to be marked. So there are 4 questions, and they don't cover reinsurance. So you should be able to do everything on this now. So I don't think there's anything more to say about that either. Unless there's any questions.